I want to keep it quick. I just want to highlight some of the new features we have in scikit-learn. Actually, a lot of the things we did over the last year were very community-focused, and I don't really have that many slides on that, unfortunately. One of the things that we established is, or the people in Paris, scikit-learn team in Paris established a foundation that actually allows them to hire 3 people full-time. So they have a non-profit at INRIA that is sponsored by industry mostly. So they have industry partnerships that allow us to hire 3 full-time developers. Also, within the last 2 months, I think, Anaconda has hired 1 core developer for us. And I have 2 core developers on staff now, so we have a total of 6 full-time core developers now, which is like quite a lot more than we ever had. But so let me come to some of the technical issues first. So what Nicolas Huygh from my team did was work on extreme gradient boosting. There's a new class in scikit-learn called hist gradient boosting, which is way faster than the gradient boosting we had before, and is like nearly the speed of LightGBM. It's mostly based on what's implemented in LightGBM. So if you used LightGBM or XGBoost before, the new implementation in hist gradient boosting in scikit-learn is definitely worth trying. We also worked on model understanding and inspection. There's a new inspect module. Right now it has only partial dependence curves now for any estimator, but soon it'll also have permutation importance, and we'll add more plotting utilities. So I think model understanding and model inspection is something where we started working on already, but we'll do a lot more. In terms of community, 2 things that I really recommend you check out is we also within the last year, created a roadmap and a governance doc. So these are 2 new things that we have never had before. So for the first about 10 years, there was no roadmap and no governance. Now we have them. I think it's quite helpful. And so, I mean, there's tons of other things that we worked on, but I only have 3 minutes and like 20 seconds now. So the thing that I'm really interested in that I want to work on in the future is better pandas support and integration with feature names. Right now, because scikit-learn is all NumPy array based, it's very hard to pass on any metadata about your data during a scikit-learn pipeline, which is very inconvenient. And so I want to at least propagate feature names through pipelines so we can make model inspection easier. Right, thanks.
And up next, we have Soo-Kwon to tell us about Numba.
So hi, I'm Soo-Kwon, and I'm a lead developer of Numba. So what's new for Numba in 2019? So I bet a lot of you know that we support like x86, 64-bit, 32-bit, but then in the last kind of 12 months, we've added more support. Like we now do CI building testing on Power 8 and 9 for 64-bit Little Endian. Your Raspberry Pi should work with 32-bit ARM v7, ARM v8. So if you have Jackson Nano, that will work. But we have a question is like, how would we provide wheels for these platforms? There's no standard, there's no Many Linux 1 spec or 2010 spec for these, so we want your feedback to how to help you get wheels for these kind of platforms. The other thing that is less known is we now support GDB. So in Python, you debug, you say you have the PDB, the Python debugger. If you're on Linux and you have did kind of traditional C Fortran programming, you have used GDB. And now you can actually from Numba import GDB, use it like the PDB. So you can call it as like the function. It will attaches the GDB process into your Numba jitter function. From there, you can just step over your source code. Yeah. With a caveat that because of LLVM optimization, you will see it jumps around because the instructions go like reordered randomly for optimizations. The other thing is some of you want like a progress bar in the middle of your compile function because it runs a long time. You can do that with object mode blocks. What we will do is we acquire the skill, jump back into Python interpreter to call that little part where you like update progress bar, do matplotlib in the middle of your hot loop. There's something you can do. And we have strings. You can have Unicode emojis inside your number functions. They will not be any faster than your CPython strings, and we only do very basic things like methods handing off of the string type. Well, 1 minute. So dictionaries, we have now a typed dictionary in number is the same Py37 ordered hash table. We will have the same performance, same hash values. We duplicated the hash of Python. It's the same implementation, you get the same value, same ordering, and surprisingly, it's actually 2 to 10x faster than the CPython the CPython dictionary. Next, the most important thing on here is we are looking to deprecate object mode, which is currently the default. Like if you can't compile, it falls back into a mode that we call object mode, which is doesn't help much. So we are looking at deprecating it as a default. It will still be there, but the default will be always compiled to no Python mode, which is all assembly fast code. I guess that's it.
And next up, we have Wolf telling us about Python.
Yeah, hello everyone. I'm not Serge. Serge is at a week-long Taekwondo thingy, so I'm replacing him. And for those of you who don't know about Python, Python is a ahead-of-time Python compiler. So if you want to use Python to speed up your numeric Python code, you can see here, it's just plain Python. Basically, you can import NumPy and use NumPy, and then you annotate it with a little comment above, where you export your function and you type the function with like the array types here, and then you compile it on the command line with Python, whatever your script name, .py, and it's going to generate you a native module which has about a 6 times speed up compared to CPython and 9 times speed up if Python is using the library that I also was working on, which is called XSMD. And so Python has quite a bit of history by now. It was came to be about 6 years ago, first presented at SciPy 2013. And the core ideas are the ahead-of-time compiler, as I said. It's embedded inside of Python. So you got pure Python and then these little bit of type comments. So very easy to use. There's a lazy evaluation of NumPy expressions, and it can optimize high-level kernels without using loops, but you can also use for loops, and they are also going to be very fast. It supports most of Python's functional aspects. You get the automatic vectorization, and you can also do parallel loops using OpenMP and have a no Python mode. And and all of that is still true today. And now 6 years later, we've got Python 3 and Python 2 support. It works on Linux, OS X, and Windows. It's on Conda, and it supports C++ code generation. So you could even extract a binary that doesn't depend on Python anymore. We have efficient support for NumPy broadcasting, and a lot of the NumPy core functions are implemented, and lots of tests are there, and you can produce a global interpreter log-free code. It's integrated deeply into the ecosystem. You can use Jupyter Notebook Magics to generate Python code. You can even use it in Python by annotating with npy mpython, and then all your NumPy calls are going to be vectorized by Python, which is going to make it even faster. And you can create capsules to use in the SciPy ecosystem, for example. And here you see some kernels. For example, yeah, you see that you can use NumPy functions and so on. And yeah, that's how much happened. Thanks.
All right. Up next, we have Marius to tell us about the current state of Condaforge.
Cool. Hi, I'm Marius. I'm a core maintainer on Condaforge, along with about 20 other people. We're a big team. So a little bit of stats. So we've grown a bit over the past few years. So we've got more than 7,000 packages now. We've got probably close to 1,500 contributors, and we're adding new platforms. So recently we've started building out ARM and Power, and we've got packages in basically every programming language that kind of matters. So we've got a lot of packages, and it turns out they depend on each other fairly heavily. So managing this kind of ecosystem globally is what we do, and we've been sort of working towards a lot of global movements in this, if we want to say, replace large portions of this. And we've done this over the past year. So we want to be with the one-stop shop for sort of like all packages. And particularly with a focus on science, we care deeply about reproducibility and research, and we want to make it easy for people to do scientific things with packages, and we want to make it easy for people to maintain and author things. So to do that, we've taken a lot of effort to have high degrees of interoperability with the default set of packages that you get if you just use the Anaconda distribution. And we can sort of scale our CI, and we don't really have, you no longer wait 12 hours to get a build for a Condaforge package. So we have a bot. The bot now just basically does most of our work. And so whenever a new package arrives and you've made a new release, we have a bot, it'll pick it up, and it'll say, it's like, hey, there's a new release of SciPy. I'll make a PR, I'll do the thing, CI will kick off, it'll tell you if it's green, it'll add all the maintainers of the recipe as reviewers, and they'll see that something's happened, and if it's green, you can go merge it and life carries on. So we've got some status pages for large-scale migrations that we do. So if we do things like, say, we want to move OpenSSL forward from sort of 1.0 to 1.1, then we can do this globally for the entire ecosystem. And we've done this by building these sort of tools to do this, and we can rebuild the entire stack in the right order. So you have to build them at the beginning, and you start at make, and then you just end it wherever you want to go. So we've switched most of our pipelines to Azure pipelines over the past year or so. So we've massively scaled our ability to be able to use CI effectively, and we no longer really wait for anything, which is great. So you may have seen this. Condaforge is a victim of its own success. We have lots of packages, which unfortunately means you have a very large solution space to pick from. So, and over time, this has mostly just gotten worse. But if you install the newest version of Conda, this is a lot better. So I would advise you, if you're waiting a lot of time for solves, just install Conda 4.7. It's a lot better, and it's going to continue getting better with some ideas that we have around sort of pruning bits of the channel that are sort of not necessary for you at any given point in time. So we haven't stopped. We're going to build more things. So we're going to make Conda faster. We're going to have GPU packages. So we're working together with NVIDIA so that we can get GPU builds of most of the standard things that you'd want in GPU packages. So things like CuPy and PyTorch and so forth. We're building out ARM and Power. So if you have particular packages that you would like to exist on ARM and Power, come find one of us. Right now, we're not building out everything, but we've built out sort of a baseline of about 500 or so packages. So if you want more things, tell us, and we'll add them to the stack. We're going to add Python 3.8 real soon. and we're going to remove Python 2.7. So we're not going to remove the packages themselves, but we will stop building new ones and automate more things.
And next we have Paige and Taylor to tell us about TensorFlow and Keras.
Excellent. And do we have a converter?
Oh, there's a.
Nah. Yes. Awesome. Cool. 10 seconds. I can count down. 9, 8, 7. The screen is turning colors. I promise I'm plugged in. Yeah. Awesome.
Thank you.
Cool. Beautiful. So hello, everyone. I'm Paige, and this is Taylor. We're part of the TensorFlow team at Google, and we're here to tell you a little bit about TensorFlow. And in case you don't know what it is a numerical computing framework that's used very extensively throughout Google. It was open sourced in 2015, and since then we've seen really incredible growth, both in terms of the people who have contributed and also the way that it's been used around the world. So if you tried to use TensorFlow in 2015, it looked a little bit like this. It was very painful. It did not look very Pythonic in the slightest. You would create variables, but you could not immediately use them. You would have to create sessions and then initialize variables and then start these weird things called queue runners. So that was bad. And the good news is that we've learned a lot since the first implementation of TensorFlow. So we've decided to standardize on something called Keras, which is a high-level API that's quite a bit friendlier. I get a question a lot of what is Keras, standalone Keras versus TF Keras. And TF Keras is really a superset built into TensorFlow and hyper-optimized for the framework. Keras.io is a standalone version that does not have support for things like distributed training and also doesn't give you all of the low-level integrations with TensorFlow that you would see. Looks a little bit like this if you wanted to implement a neural network. So for example, MNIST classification, handwritten digits from 0 to 9. It's about 10 lines of code. If you wanted to scale that across a cluster of machines with GPUs or TPUs, all you would have to do is define a strategy and then place your model within a strategy scope. With TPUs, you would just be toggling out mirrored strategy with TPU strategy. And if you want to, yeah, go for it, dude.
Yeah, one thing I want to call out on on this example. So one really common pattern you see is softmax followed by cross entropy. That actually has terrible numerical properties if you do them separately. But one of the things that Keras will do for you is it will actually identify that pattern and replace it with the more efficient softmax cross entropy with logits.
Excellent. And we are also including something in a couple of months called Keras Tuner that'll allow you to do hyperparameter optimization with Keras as well. So stay tuned for that. You can make it even faster by wrapping things in TF functions. This turns all of your dynamic computational graphs into static computational graphs. And with TensorFlow 2.0 beta, we've decided to focus on usability. So there's eager execution by default. TF data makes it easy to use NumPy arrays as part of your deep learning models.
And this is something that has improved substantially from 1.x. If you wanted to get a NumPy array through TF data in 1.x, there was a fast way and an easy way and an efficient way, and they were very far apart. We've now combined them so that in 2.0, the fast way is the easy way.
Excellent. So we've borrowed a lot of ideas from scikit-learn. They did a lot of things correctly, and we're trying to follow suit. We've standardized across something called a saved model. So you build a model once, you can deploy it across mobile and embedded devices, browsers, servers, whatever. We have access to all of the low-level ops still. Everything is run as part of an open design review. So if you want to get involved with any of our special interest groups or make proposals to change the API, we encourage that. heavily. We've integrated TensorBoard with Jupyter Notebooks as well as with Google Colab, so it's embedded directly within the cells. We've added built-in performance profiling for GPUs as well as TPUs. We've improved API documentation and are starting to run community doc sprints. And we've also created a completely open and transparent project tracker. So if you want to keep up to date on status for any of our issues or bugs, you can follow along on GitHub. Free resources available for you to try out. Deep Learning with Python by Francois Chalet, who's the author of Keras, as well as Hands-on Machine Learning with Scikit-learn and TensorFlow by Aurélien Guérin. We also have a free course available on Udacity and a whole bunch of guides and tutorials on tensorflow.org/beta. So that's it. Please install it. Tell us what you like. Tell us what you don't. And thank you for your time.
Come on. All right, and our last speaker of the session is Ivan to tell us about PyTorch.
Hi everyone, my name is Ivan. I'm working at Quantization. I'll talk now about PyTorch. What is PyTorch? NED array library with accelerator support, automatic differentiation engine, gradient-based optimization package, utilities, distributed transport, just-in-time compiler, a NumPy alternative, also deep learning and reinforcement learning. Basically, there is the C++ code and the Python bindings. The ND array, the tensor library, is pretty similar to NumPy, very fast, and it has a very fast acceleration. Automatic differentiation, the ability to take nth order derivatives, the ability to do in-place operations. Neural networks. In eager mode, it's a Python. The Python is the interpreter and VM. In JIT mode, torch.jit is the interpreter. Optimization package, gradient-based optimizers, PyTorch JIT compiler, goals, production needs, and global optimization. Eager mode, it's simple, debuggable, hackable, needs the Python interpreter, and difficulty to optimize. And PyTorch script mode, optimizable, production deployment, and compiled and run by the Lean just-in-time interpreter. Eager to script mode with torch JIT trace. Eager to script mode with decorator torch.jit script. Exporting a model to production. Torch script models can be saved a model archive and loaded to run in PyTorch just-in-time compiler instead of CPython interpreter. There's a lot of slides, 40. Sorry for that. What kind of optimizations do we do? Algebraic rewriting, out-of-order execution, kernel fusing, target-dependent code generation in maintaining the same semantics is critical for users' experience. There is Torch distributed in sync mode and async mode. And third, Torch and distributed data parallel. Pretty easy to use, just wrap your model. C++ extensions, it's pretty similar to Python code. There's some updates in the PyTorch as named columns, RPC, and one more. I forgot the name. And quantization. Thank you so much.
All right, and that is the end of the final plenary session. If we could have a round of applause for all of today's speakers. And all of the speakers from the previous 2 days. And I realized I never introduced myself. I'm Thomas Caswell, and I'm one of the co-chairs, and Hannah Eisenman is the other. All right. Thank you all, and see you next year.